All right, welcome. Today, we are pulling back the curtain on a piece of technology you've probably never seen, but believe me, it powers pretty much every aspect of our modern world. It is the true unsung hero of industry, so let's just dive right in. So just think about this for a second. Deep inside refineries, chemical plants, and power stations, there's a device that is absolutely critical to making everything, well, run. It's kind of like the circulatory system for all of heavy industry. Any guesses what it is?
You're looking at it, the shell and tube heat exchanger. Its job sounds elegantly simple, right? Just transfer heat from one fluid to another without those fluids ever actually touching. It might sound straightforward, but its role, especially in the oil and gas industry, it's massive.
Okay, so before we get into what can go wrong, and trust me, the high-tech fixes are really cool, we first need to get a handle on exactly how this industrial workhorse actually gets the job done.
So the whole thing is broken down into just a few key parts. You've got the outer shell, which is kind of like the body, and inside that, there's a tube bundle. That's really the heart of the whole operation. And then you have these things called baffles, which act like little traffic cops, directing the fluid to flow all around the tubes to make sure we get the most heat transfer possible.
The whole process is basically this simple three-step dance. First, a hot fluid, let's say crude oil, flows through all those inner tubes. Second, a cooler fluid, maybe water, flows in the outer shell surrounding those tubes. And then, step 3, this is the magic. Heat energy literally jumps from the hot fluid right through the metal tube walls and into the cooler fluid. All of that happens without a single drop ever mixing. And look, these machines are not just sitting in some quiet lab somewhere. They are built to be incredibly tough, handling extreme pressures and absolutely scorching temperatures. This is exactly why they are the go-to choice in these super demanding environments, where, failure is just not an option.
But of course, even the toughest workhorse has its enemies. And for the heat exchanger, the biggest threats actually come from the inside out, waging this constant, relentless battle against its performance. So here they are, the 4 main villains of our story. Fouling, think of it like cholesterol in an artery, just clogging up the whole system. Then you've got corrosion, that slow, silent decay that just eats away at the metal. And then, of course, there are the outright failures. We're talking cracks in the tubes or leaks in the seals that can bring an entire multi-million-dollar operation to a grinding halt.
And just look at the impact of fouling alone. It is staggering. When an exchanger is clean, you get high efficiency, normal pressure, low energy costs. Everything's great. But a fouled one? Oh man. Heat transfer just plummets, the pressure skyrockets to dangerous levels, and the energy costs go through the roof. This isn't some minor inconvenience. It's a massive, massive drain on both productivity and the budget. So what is this fouling exactly? Well, it's not just one thing. It can be hard, crusty scale, kind of like what you'd find in an old kettle, or it can be a thick, waxy buildup from crude oil, or even stubborn, rusty corrosion products. Basically, it's all the industrial gunk you can imagine that just chokes the life and the efficiency right out of this critical equipment. So, how in the world do you fight back against these enemies? You can't just go in there with a wire brush. No way. This requires a high-tech tune-up using a specialist toolkit that's basically designed for industrial warfare. The entire process really rests on these 3 pillars. First, you've got to find the problem, and you do that with advanced inspection. Then, you launch an all-out assault with specialized cleaning. And finally, you have to put it all back together with absolute surgical precision. Think of this first step like a medical checkup for the machine. Specialists use these incredible tools like borescopes, which are basically tiny cameras on long, flexible tubes, and ultrasonic probes to see deep inside the tube bundle. They're looking for hidden cracks, corrosion, and blockages that are completely invisible from the outside. Okay, once the problems are diagnosed, it is time to bring out the heavy artillery. We're talking chemical baths to dissolve the really stubborn scale, and hydrojetting. This is basically a pressure washer on steroids, hitting deposits with water jets, blasting it over 10,000 psi. For oily sludge, they use hot oil flushing. For waxy films, it's vapor phase degreasing. Each method is a specialized weapon chosen for a very specific kind of gunk. And even after all of that, the job is far from over. I mean, getting it clean is one thing, but putting it back together perfectly, that's a whole other ballgame. Technicians use these incredibly precise tools to torque and tension every single bolt to the exact right specification. The goal here is simple, a perfect, leak-free seal. No exceptions. But you know, the best specialists, the real pros, they don't just fix the problem and call it a day. They aim higher. They're always looking for ways to restore the machine to its absolute peak performance, and sometimes even make it better than it was before. And this is where the science really takes over. Teams analyze all these key performance indicators to actually measure their success. They want to maximize something called the LMTD, which is just a fancy way of saying they're getting the absolute most out of the temperature difference between the fluids. They also want a high U value, which measures the overall heat transfer rate. And crucially, they need to minimize the fouling factor. That number tells them just how much that gunk is resisting the heat. It is a completely data-driven approach to optimization. And all that data, it leads to smart, proactive upgrades. They might recommend swapping out the tubes for a more corrosion-resistant material like titanium, or maybe modifying the internal baffles to get better fluid flow. The goal isn't just to clean the machine, it's to make it more robust and more efficient for the future, to stop these same problems from just happening all over again. So we've gone pretty deep into the mechanics and the maintenance, but let's pull back for a second and look at the big picture here. Why does any of this really matter?
It matters because the ideal solution is to have one single unified team handling the entire life cycle of care for this equipment, from that very first inspection through all the cleaning and repairs, all the way to the final testing and getting it back online. One team, one responsibility. It just makes sense.
Because we're not just talking about one piece of equipment here, not at all. A single failure can trigger a huge domino effect, disrupting production and creating instability all across the system. So keeping these exchangers healthy, it's fundamental to the integrity of our entire energy infrastructure.
The payoff for all this meticulous work is huge. First and foremost is safety, preventing leaks or failures that could be incredibly dangerous. But right behind that is efficiency, which directly translates to using less energy and spending less money. And all of that leads to reliability, keeping these crucial plants running smoothly and protecting our energy supply.
Ultimately, it all comes down to this really powerful mission statement. Zero harm, zero leak, maximum integrity. It's a philosophy that just perfectly underlines the incredibly high stakes of this kind of work.
So, this complex, high-stakes dance of maintenance on these hidden engines is what keeps our lights on and our cars running. It really makes you wonder, doesn't it? What other complex, totally invisible systems are out there, humming away just out of sight that we completely take for granted every single day?